talk about actually integrating moment of inertia and how you calculate moment of inertia for any object, which is now your new superpower. So moment of inertia is just going to be, we're just rewriting it. Remember, when we did it as a summation, it was just x squared times m for each piece. Now, remember, r we call a dummy variable, which just means this can be x or y or z or any of those things, okay? So for instance, for a thin rod about the center, if we pick a little piece dm over here or dx, you know, with a mass of dm, it's got a distance r from wherever you're calling 0, okay? And then you're just going to add up those things. So in this case, this would be r, in this case, this would be r. And let me show you what that means in terms of actually setting up the integral. And I don't know, personally for me, this is very exciting as someone who wasn't that stoked on calculus, because I was like, why are we doing all these integrals and where the heck did they come from? Like, the book didn't just like magically generate these problems that we had to solve. And in physics, we get to make the problem and then you have to remember how to solve it using calculus. But we're making integrals from scratch, which I think is pretty exciting. And maybe, I don't see a lot of excitement out there, but maybe there is, like deep down in your math physics soul, okay? So we're going to try this out. We're gonna calculate things we already know again, just to show that we can, okay? We know what the moment of inertia is for a thin rod pivoting about one end. Does anybody remember what that is? Oh, the center is 1/12. The end is 1/3, okay? So we know we're gonna get 1/3 ml squared, okay? But how did the book get 1/3 ml squared? Well, we're gonna do what the book did to get that, okay? So let me walk you through that. And I'm gonna go through this pretty slow, and stop me if there's parts that you don't understand, because this is a new concept, but it's never gonna go away. So like the whole next semester when we start electricity and magnetism, we do this a lot, like this technique of setting up integrals. This comes up a lot. So if it comes up for moment of inertia, it just comes up in physics a lot. So stop me, it's the new concept, but the more we do it, the less horrible it will be in the future. So we're gonna first draw a picture. So we have a long, thin, uniform, we've been drawing a lot of sticks. So let me draw a stick. And it actually worked. That's exciting. So here's a long, thin rod of length L. Let me just move it over a little. And here's the x-axis, okay? And we want to mark the 0. Here's 0 over here, and here's L over here. We know that the moment of inertia equation looks like this, okay? And this looks a lot like what we did for the center of mass calculation. So we're just gonna start by remembering that this is basically chopped up into a bunch of little pieces. Sorry, they should be evenly spaced, but you get the idea. They all have a length dx, and why is it dx and not dy or dz? Because we're on the x-axis, okay? And each of these has a mass dm, okay? Now remember, we have to calculate things in terms of dx. So when we go back to this integral, we know since this is on the x-axis, we have x squared, and that's this distance, right? So there's always a distance from 0. In this case, this is x. And if you picked a piece over here, this would be x. If you pick a piece over here, this would be x, right? X is variable. That's why it's the variable we're choosing. It's x because we're on the x-axis. If we were integrating along the y-axis, this would be y and a dy, okay? It's really that simple. So for dm, we know that dm, right, should be equal to m over L, the density, times dx. Just like we did for center of mass, okay? So everybody understanding why we're converting dm to dx and how we're doing it. So this is just density, mass divided by length times length. okay? Mass divided by length times length, it gives us mass again. So for dm, we plug in m over L dx. And part of the reason we do this is because we need to integrate over x. So we can't leave it as dm, okay? What do you think our limits of integration are here?
0.
Yeah, because we're gonna integrate from here, right, this piece, and then we'll get this piece, and we're gonna integrate over the whole thing until we get to L, okay? So we're integrating from 0 to L. That means we're integrating over the whole rod, okay? And so for each piece, we're just taking a dm, and then a dx, and then we add another dm, and another dx, and then we add another dm, and another dx as we get larger and larger. So from 0 all the way over to L, okay? Cool. So now we're just doing some math. So we'll pull the m and l out, and now we just have 0 to L x squared dx. And just as a reminder, what answer are we thinking we're gonna get? 1/3 ml squared. This is what we know the answer is going to be because we read it off the chart earlier, okay? So we do this integral. Integral of x squared gives us 1/3 x cubed. You plug in our limits of integration, so we get m over L squared, 1/3 L cubed, okay? And let me just move this up. Two of these are going away, and all of these are going away. So we get 1/3 ml. I lost something. Oh, that wasn't squared, that's why. So this becomes a 2. Yeah, it's 1/3 ml squared. Is this what we were expecting to get? Yeah. Okay. Any questions about that? Do you guys understand the density part? Hopefully. All right. We're gonna have you guys try doing one of these. So I want you to do the same calculation this time, but for a rotation around the center, okay? And what answer are we expecting to get there? You remember that one? Come back to the chart. If you're rotating, yeah, it's the 1/12, right? So you know we're gonna get 1/12 ml squared. So figure out how to reset this thing up. It starts the same way, but you have to draw it slightly differently. Take a couple minutes and see if you can get this one set up.
That's what I'm doing.
Oh, that's pretty good. Your limits of integration are, so the key thing here is 0 always goes on the axis of rotation.
Okay.
So in this case, when you draw it out, you want this to be 0, which
Yeah.
means this is negative L over 2, and this is L over 2.
Okay. So the end part is L over 2?
Yeah, and so that's the only thing that's different between this case and this case is the limits of integration.
Okay.
Okay, we ready to go over this?
Yeah.
Alright, so remember, this is the answer we know we're looking for because we already know that's what's in the book, okay? So the main thing to remember here is when you're calculating moment of inertia, where do you put 0?
Center?
Not necessarily at the center of mass, at the point of rotation, okay? So you always want to start with your 0 at the axis of rotation. So before we had our 0 at the end of the rod because we knew it was rotating about the end. So if we're rotating about the end, we put 0 here. If we're rotating about the center, we put 0 at the 50 centimeter mark, okay?
Yeah.
So we draw the same thing, and actually I'll just copy this over. Oops, that's not what I want to do. Oh boy, okay. Copy, there we go. We paste this thing over here. So it's the exact same thing we had before. but the difference now is we set it up so that this is still the x-axis, but now 0 is right here, okay? Which means that if you're setting something with a length L with 0 in the middle, this is going to be L over 2, and this is going to be negative L over 2. And this is important because we're still integrating from end to end, but it changes the limits of integration. So in this case, when we calculate our moment of inertia, and this is r squared dm, we know that this is the x-axis, so we call it x squared dm. Remember, dm we calculate as, it has to be in terms of dx, so we call this m over l dx. That's because for each little chunk of stuff that has a mass m and a length dx, right? So mass dm, length dx, we're calculating the density times the infinitesimal mass, that's dm, that gives us this dx piece, okay? Now we're calculating this from L, oh sorry, let me move this m over L out. From negative L over 2 to L over 2 of x squared dx, okay? Remember, what we're doing is we're still doing an integration from here to here. So that means for each of these little pieces, you'll have this, and it's gonna have a distance of like negative L over less than L over 2, and then it goes to another piece over here, and that's gonna have a shorter distance, and then here you're gonna have almost 0, and then you keep adding up pieces till you get over here. So you're integrating across this whole thing. Very messy, okay? But the integral looks essentially the same as before, so we know that this gives us m over L of 1/3 x cubed from negative L over 2 to L over 2. Plugging this in is more annoying now, and we'll pull the 1/3 out. So this becomes L over 2, oh it's cubed, yeah. Right, yeah, minus negative L over 2 cubed. Algebra happens, so we end up with m over L 1/3. This is going to be L cubed over 8 minus negative, so plus L cubed over 8, right? So we end up with m over L 1/3 times 1/4 L cubed, okay? So this gives us 1/12. We get rid of one of these L's, so that's squared, mL squared. And that's what we were expecting to get, hopefully. Okay, everybody following that? All right, so whenever we do these problems, we look at this, okay? We figure out what axis we're on, that tells us our R. We figure out the density, that gives us our conversion from dm to whatever spatial coordinate we need, so the little infinitesimal length of something, and then we just figure out our limits of integration based on our drawing. We set our rotational axis to be 0, and then we just integrate. Okay, the rest is primarily algebra. Cool. Any questions about this? Because it is new and foreign. So what would you do if we wanted to calculate the moment of inertia around like 20 or 30 centimeters?
Change where the 0 is.
Yeah, you change where the 0 is to somewhere over here, and then you would change your limits of integration, so you'd probably be integrating from like L over 4 to 3L over 4, right? Negative L over 4 to 3L over 4, something like that, okay? So you just have to do some new fractions. But if you have this one, anywhere else you could use the parallel axis theorem. Would the parallel axis theorem work if you wanted to move it from the center to the end? Yeah, anything, anywhere you want to move it, the parallel axis theorem works. So you don't have to do a whole nother integral if you're using the parallel axis theorem. So that's why that's useful. We introduced that first because it's a lot easier than setting up the integrals. Okay. Cool. Well, that's all I got for today.